look at logarithms as kind of an introduction. And so before I get too much into it, I want to go over a little bit of history here, notation. So, you know, mathematicians, they would say, okay, I have a base, and I'm going to cube it, and I'm going to get 8. And I say, what's that base? And, oh, well, that base is 2. 2 times itself 3 times gives you 8. And I got a base, and I want to cube it, and I want to get 27. What's that base? And I say, oh, well, okay, that base is 3. 3 times itself 3 times gives you 27. They go, okay, I got a base, I want to cube it, I want to get 11. Well, you begin to see what part of the problem is here. Um, that uh, there isn't a clean number that gives us that you cube to get 11. It's somewhere between 2 and 3 because 11 is between 8 and 27, 2 points something. But what we find is it's a non-repeating, non-terminating decimal, an irrational number. So since it's a non-repeating, non-terminating decimal, you can't really write it easily. So mathematicians came up with some notation, and the notation we have settled on is this root notation, that the number that you cube to get 11 is the cube root of 11. So in other words, if you take the cube root of 11 and you cube it, by definition, you have to get 11. And so, that's a way we came up with some notation to describe that type of irrational number. Now let's say we have 5, and we take that to a power, and we get 25. And say, what's that power? And you say, well, that power is 2. 5 squared is 25. Okay. And say we go 5 to a power, and it says 125. Well, what is that? Well, that power is 3. 5 times 5 times 5 is 125. And then we got 5 to a power, and we get something like 31. Well, what we find is, again, there's not a nice number. It's somewhere between 2 and 3 because 31 is between 25 and 35, probably a lot closer to 2 than it is to 3. But it's a non-repeating, non-terminating decimal, so we need some notation to use. And the notation we have settled on is this logarithmic notation. The power of 5 that gives you 31 we call log base 5 of 31. So the little subscript here describes the base we're working with, and then the number inside of the log, as we say, it's inside, like this is 11 is inside this root. We say this is inside the log. If you wanted to put parentheses here, you can put parentheses like that. Inside the log is 31, the answer you would get. So if you took, by definition, if you took 5 to the log 5 of 31, you would have to get 31 as an answer. So as long as these bases matched, this would give you the number inside. So if you had, what's 3 log 3 of 28, that would have to be, by definition, 28. So we know, though, like if I could say, what's 3 log 3 of 9? We say, well, that's 9. But we know that 9 is also 3 squared. So since these bases are the same, and we're saying these statements are equal, that must imply that log 3 of 9 is the number 2. And so just like, like if I said, what's the cube root of 8, you would say that's 2. Some roots can break down, and some logs can break down into nice numbers. This connection here between a format where you write things as an exponent and you write things as logs, and logs are exponents. So if you keep that in mind, that logs are exponents. So this statement is kind of this, this, we call this the exponential form, this first one here. That statement is, kind of more the normal notation, with 3 as a clear base number, and 9. Whereas this second one is a log notation. It's really a statement about the powers. It's really saying this power is the same as this power, right? So that's really what this statement says. It's saying those powers are the same. So this gives us a way of describing two relationships. We have what we call exponential form, and we have what we call logarithmic form. Logarithm. I'm gonna. Yeah, there's no R there. That's the problem. Okay. Can't write. Logarithmic form. I kind of thought myself there. All right. Sorry. So in exponential form, you have a base, you got a power, and you got a value. In logarithmic form, you have log based on the base of the value equals the power. So in my example up here, 3 squared equals 9 can also be described as log base 3 of 9 equals 2. And so we can convert between these two formats. These formats are giving me the same information, just in slightly different ways. This first one, if I wanted to say this in words, I would say 3 to the second power is 9. Okay, so that's kind of what that's saying. And here, this is saying the power of 3 that gives you 9 is 2. So the power of 3 that gives you 9 is 2. And, well, yeah, 3 to the second power is 9. So these statements are the same statement, just in slightly different formats. And this gives us a way to convert. Sometimes things work better in exponential form, and sometimes they work better in logarithmic form. So we're going to be asked to simplify some things. But before that, I want to talk about some special logarithms. And so we have what we call the common log. This is log base 10. So a lot of times you'll see log base 10, like log base 10 of x, and you'll see it actually written as just log x, or log 3, or whatever number you have there. So if you don't see a base number, you're to assume the base number is 10. And sometimes, some books or some problems will write the 10, and sometimes they won't. This is, again, comparing this to ideas of roots. We have things like cube roots and fourth roots and fifth roots. But if I just write a root symbol, I don't give you a number, you're supposed to assume there's a little 2 up here that I'm not writing. It's a square root. And so it's because we use that root so often that we just say, okay, if there's not going to be a root, if there's not a number there, then you're supposed to assume it's a 2. Same thing here, is if there's not a number, it's supposed to be a 10. So if you intended it not to be 10, then you forget to write the correct number, then you would get it wrong because it would assume, oh, you're talking about 10, and you weren't. The other special log is what we call the natural log. And this is log base e. So again, I'll just say of x, of some number. And so what you'll see is, almost never see it written in log base e. Instead, e is what we call the natural base, used for natural systems. And so, you're looking here and like e wants to be special. It doesn't want to be like everybody else. Log base 10, log base 3, so it says, okay, well, why don't you just, when you say log, that would be me. And 10's like, no, that's me. I already got that. I picked that. And so e's like, I'm going to be continental. I'm going to be fancy. I'm going to be log natural. Log natural. So when you say log natural, natural log, you're talking about me, log base e. That's the only thing different about ln, is that it's just log base e. The e is not, you don't write the e, it's understood. So if I said, what is ln of e squared equal to, you would say, what this is saying is, what power, this is what the log says, what power of e gives me, and then what's inside? E to the second power. So what power of e gives me e squared? So remember, I'm talking about a power. What is the power? And the answer to that is 2. The power of e that gives you e to the second power would be e to the second power. So this first e, if I wanted to write it out, in kind of a more standard notation, it would look like this. So e to the second power gives me that. That's how that log notation works. So, you know, ln's a special one. So this kind of brings us into, you know, evaluating logs. And so, you know, if I said, okay, tell me what value each of these logs are. So I have log base 3 of 27. And again, what I'm asking for is the power or the exponent here. That'll give me what power of 3 will give me an answer of 27. And that is 3 to the third, right? 3 to the third is 27. And so what I'm getting, what this is the exponent. That's what it is. It's the exponent. All right. So if I say, okay, what's log 2 of 1/8? Well, the answer to that is -3, right? Because I know if I take 2 and I cube it, that would give me 8. This is 1/8, the reciprocal. So I need to make that a negative, and that would give me 1/8. So remember, when you're asking for what the log is equal to, we're looking for just the power. What? Just the power. Log, say, 49 of 7. What is that? Well, 7 to the second power is 49. So what exponent of 49 gives you 7? 49 to what gives you 7? Well, the square root of 49 is 7. So how do you write the square root as an exponent? And the answer is you write it as a fraction. So this is the square root, the second root. This is the 1/2 power. So again, logarithms are exponents. So you need to know your rules of exponents. The way to figure out these things are using your rules of exponents to do it. Now, all right, so now let's say I wanted to do log 3 of 12. You know, what's that? Well, at this point, I can't do it. I don't have enough information. I need to learn some more things about logs to figure this out, because this is asking what power of 3 gives me 12, and I don't know one right off the top of my head. And most calculators cannot do base 3. Some can. Some of the more advanced ones can, but most calculators cannot, even scientific calculators. But it can do some value. So if I said, you know, I want to approximate to the nearest thousandth, okay, log 27. Well, that I can probably do in a calculator, because my calculators usually have a log button, and log, that's base 10, so log of 27, so 1.431, right? 431. Oops, I guess approximately, right? Or if I said ln of 6, what is that approximately? So my normal calculators usually have an ln button, ln of 6, put that in there, 1.792, 1.792. So, you know, I can do some approximate values as long as the base is, you know, it's using the common log or the natural log. If it's using a base other than these, like this, you know, what log base 3 of 12, well, I don't know what that is. I can't figure that one out. And then let's talk a little bit about graphs of log functions. Actually, let me save this for another video. Let me just stop there.